Hi, this is a video about the Monty Hall problem and kind of taking a look at it from both an intuitive standpoint, which is really easy to understand without any additional math, and just kind of walking through all the different scenarios and hopefully convincing you of why the surprising result is true, but then also taking a look at it from the perspective of Bayes' theorem, which is going to allow us to more rigorously prove mathematically why we have a greater likelihood of getting the car if we switch doors. So I like to start by going down the route of trying to understand this intuitively without any math, just kind of walking through all the different scenarios. So I've kind of drawn really bad diagrams of depicting, the two different scenarios that can happen in the problem. So again, you either have a car behind one of the doors or you have a goat. Yes, that is my attempt at a goat. It's not quite an artist, but it's a creature. It's an animal. And assuming you don't want the animal and you want the car, that's the idea here. And for the sake of simplicity, all the door numbers here are just going to be arbitrary because you could just easily relabel those. They're just labels, nothing more than that. So door 1 can be door 2 can be door 3, so long as we're consistent throughout the problem. They're just labels, and so for consistency, I'm going to say we always choose door 1 initially. That can be assigned as our initial guess. The physical location of that door on the game show doesn't really matter, right? So we're just going to call the door that we guess initially door 1. And there's two scenarios. Either the door you guess has the car behind it or it doesn't. And yes, you could argue that, the door, if the car is not behind your door, there's still two other possibilities where it could be behind two other doors. But we'll notice that it doesn't really matter whether it's behind door 2 or door 3, the outcome is going to be the same. So looking at it from the perspective of first, the door you chose has the car behind it. So good job, your first guess was correct. That means that you're going to be choosing door 1. So I'm just going to indicate that here. This is the door we are choosing. So that's the door we chose. And then the door that Monty is going to consequently open has to be either door 2 or door 3. So any of these two doors, Monty can open either of them, right? It's up to his discretion. It's his choice, and from that perspective of human choice, we can consider that a random choice with equal probability. He can choose either door to open. So once he does eventually choose one of those two doors to open, whether that be door 2 or door 3, at that point, we then get a choice whether we want to switch or not. And so what I'm going to do is, again, what I'm trying to convince you of is the result or the solution to the Monty Hall problem, which is that it's always more efficient to switch doors rather than stick with your initial guess. And so to illustrate that point, what we're going to do is, in both scenarios, I'm going to assume you always switch doors, and then we can look at the probability or the likelihood of you winning the car if you follow that strategy. Of course, you could go about it the other way, and you just get the inverse result, but the outcome would be the same. So assuming you are going with the winning strategy, which is that you always switch doors, in this case, you're clearly going to lose out, right? Because you already chose the door that had the car behind it. So, you can either switch to door 2 or door 3, and that's going to be completely dependent on which door Monty decided to open. You switch to the other door. So these are your options of where you can switch. It doesn't really matter which door you switch to. Either case, you've lost the car. Your initial guess was right. So not looking too good for team switch, but let's go ahead and take a look at the other possibility here. So the other possibility is, again, we always choose door 1. So that does not change. Right, so we always choose door 1, but now this time there's a goat behind door 1. And the car is behind either door 2 or door 3. For illustrative purposes, I've drawn it behind door 2, but again, they're just labels. Door 2 can be door 3, door 3 can be door 2. The physical location doesn't matter. It just, it can be the car can be either behind door 2 or door 3. And for this example or for this illustration, it doesn't really matter which one it's behind. So in this case, now that you've chosen a door with the goat on it, Monty has no other option besides to open door 3, right? The other door that doesn't have the car on it. So if you chose one door and there's two doors left, one of them has a car, one of them has a goat, he has to open the other door with the goat in it because he can't open the door that has the car in it. That would give away the result. And he can't open your door because that would also tell you exactly whether you should switch or not switch. So this is the door that Monty will open. There is no question about it. which means if you follow the switch strategy, you will always switch to the door with the car. There's no other door left to switch to, right? He's opened that door, so that's door 2. You always switch to that. It's definitive since there's only one choice for which door he opens. There's only one choice for which door you switch to. Okay, so clearly what we can see here is that in scenario 1, you lose the car. So we can label this as a loss. And in scenario 2, you win the car. So this is a win. So if we then take a look at what conditions were required for each of these scenarios to take place, we can now begin to understand why it is beneficial for you to switch. So take a look at scenario 1. For you to have chosen the door with a car behind it, that's a pretty simple probability because it's not introducing yet the new piece of information about Monty opening another door. So it's a very simple probability problem, right? There's 3 doors. You don't know which one the car is behind. It's only behind one of them. You choose one at random. There's a 1/3 chance you get it right. So scenario 1 has a 1/3 chance of happening. And scenario 2, well, what's the chance that you initially choose a door with a goat behind it? Again, that could either be door 1 or it can be door 3. It doesn't really matter. Again, they're just labels. So this probability that you choose the door with a goat behind it, that's not 1/3, it's actually 2/3, right? Because there's two doors with the goats behind them. So there's a 2/3 probability that you choose a door with a goat behind it. And now if we take a second to realize what those results mean, if you agree with initially the fact that these 2 scenarios result in a loss and a win, and now you also can see that very basic probability applies, the chance that you get into scenario 1 is 1/3 and the chance that you get into scenario 2 is 2/3, then the result becomes quite evident, right? If we just highlight these boxes here, there's a 1/3 probability that if you switch doors, you lose, and there's a 2/3 probability that if you switch doors, you win. So that means if you take the inverse of that, if you follow the other strategy where you don't switch doors and you stick with your guns, then your probabilities are reversed. You lose 2/3 of the time and you win 1/3 of the time. So hopefully that's an intuitive explanation as to why the result of the Monty Hall problem, or why the solution to the Monty Hall problem is beneficial to always switch doors. From kind of the standpoint of just walking down all the cases and seeing how they play out and seeing the initial probability without having to introduce the complexity of the additional information that we were given, because that does complicate the probability quite a bit. And that's what we're going to do right now. So this was a pretty good scenario because it only had very limited options, and we were able to very easily walk through all of those options to see intuitively why the result is the way it is. However, for problems that are more complicated, it's sometimes nice to have an approach you can always fall back on that's more rigorous and more mathematically defined. And one of those approaches that I want to talk about today is Bayes' theorem. So Bayes' theorem is fundamentally is a formula or an approach that's used to update probabilities given new information. So the reason we want to use it or apply it in this scenario is that we have some initial guess about the probability of finding a goat behind a door or a car behind a door. That's pretty obvious. We've used that probability here as 1/3 there's a car behind the door we chose. But what happens is that new information is added when Monty decides to open a door and show you that there's a goat behind it, which then changes the probabilities that are in play. And so Bayes' theorem gives us a way to mathematically work that out to what it's going to be. And what we're going to see is we're actually going to end up with the exact same probabilities that we had here, where you have a 1/3 chance of picking, of losing and a 2/3 chance of winning, depending on whether you switch doors or not. So let's go ahead and give that a go. I have the formula written down here, and now we've gone to a general case. You'll notice we no longer know what's behind any of these 3 doors. We are considering it from a general standpoint. And so I have the formula written down here, but what I want to quickly do is I want to walk through what the formula is really trying to tell us, and then connect that to what it's trying to tell us about the Monty Hall problem in specific. So we can kind of imagine Bayes' theorem graphically as diverting possibilities of events. So in its simplest form, it has just two layers of possibilities. And we can call each of these as an event happening. So at top here, we can call this event A. And at the bottom here, this is the probability of event A not happening. So this is our first layer of the network. And after that, a second event happens conditional based on event A happening or not happening. So that's event B or event B not happening. And the same thing for the other case where event A is not true. So this is the fundamentals of what Bayes' theorem is trying to do. And if we look at this formula now, what Bayes' theorem is telling us is what is the probability that A happens given that we know B happens. And we have some other terms here. So that's, again, what that straight line means there. So if you kind of break this down, we can apply all these terms visually on this graph and see what they're talking about. So the probability that A happens given B, that is this guy right here. So the probability that A happens is this branch right here, right? And within that branch, we have a couple of probabilities. So the probability of getting to this stage of the branch, well, that's just the probability of A. This one is of A not happening. So the probability that you get A is going to that branch. The probability that you get B, assuming you knew that A has happened, so you're already at this point, what's the probability you get to hop to event B? Well, that's the probability of B given A. And the total probability of this entire thing would be the probability of B given A. But we don't want the probability of B given A, we want the probability of A given B. So what that represents there is if we know that event B has happened, what is the probability that A has happened? So it's kind of almost working backwards here. Because, and the reason this is helpful for us is going to become very clear to this problem as soon as we define what A and B are. Like, what are these events? So if we let A represent the probability that a car is behind door 1. So the event in question is the fact that probability of A, so the event A is the fact that the car is behind door 1. Okay? And we're going to let event B represent the fact that Monty opens door 2. So in other words, there's a goat behind door 2. So door 2 is open. Open door 2. Again, the labels are arbitrary, just like we saw in the previous example. And we will take into account the fact that it could either be door 2 or door 3 as we go through the math. But for now, the labels can just be reshuffled in your mind, depending on whether you want it in the middle or the right. It doesn't, or the left. It doesn't actually make a difference in terms of just the labels. And so now that we have that in place, we can really think about what Bayes' theorem is trying to tell us with this formula here and how it relates here. So what it's saying is, what is the probability of A happening, meaning the door you chose has a car behind it. So what is the probability that the door you chose has a car behind it, given that door 2 was opened, right? And we have some other terms here, and we're actually going to go compute those terms to be able to find that answer. But hopefully you realize that that is exactly what we're trying to find, or it would give us the solution to our problem. What is the probability that the door we chose has a car behind it, given that another door was opened by Monty? In this case, specifically, the label is just door 2. So what is that probability? Well, we hope to see that it's going to be 1/3, because we know that the initial door that we picked after Monty has opened another door with a goat in it only now has a probability of 1/3, and the other door will have a probability of 2/3. So we expect this result, the probability that A, the door 1, has a car behind it, given that door 2 is opened, another door with a goat behind it is being opened, should be 1/3. And that's the result we're trying to derive mathematically here. And so we're going to go about doing that by considering the terms in Bayes' theorem. So the first term we're going to consider is very simple. It's just the probability of A happening. So this one is the easiest out of them all. What is the probability that door 1 has a car behind it? That's pretty trivial. We even applied this in our intuitive application. It's 1/3, right? There's one car, 3 doors. It's behind one of the doors. The probability is 1/3. Fairly simple. But the next thing that we want to delve into, so that's, by the way, that's this term right over here. So we already know what that term is. But the next term we want to delve into is, what is the probability of B given A? And what does that mean? What is the probability that Monty opens door 2, given that the car is in door 1? So I've kind of drawn that out here. This is that scenario. And now you've noticed that we've gone from kind of unknown in what's any of these doors to now we're looking at a specific subset of the probabilities where the car is, for 100%, always will be, in this scenario, in door 1. And so now, again, this is not going to change anymore. This is fixed for this scenario. And we're now asking, what is the probability that we open this door 2? Well, we can kind of, like, how likely, specifically, how, not that we choose it, but how likely is that Monty would open that door. So if we consider this, what we realize is that, well, Monty has 2 choices here, right? Like, he can either open door 2 or door 3. it really makes no difference. There's goats behind either. He's not revealing where the car is, and he's not choosing our door. So he could realistically open door 2 or door 3. So the probability that he chooses to open door 2 is completely arbitrary. It's even, half and half, up to him. So there's really no way for us to know which one he would open, and there's no reason for us to be inclined to believe that he's more likely to choose one door over another. So from that standpoint, if the car is in door 1, and the other 2 doors would then have goats in them, the probability that he chooses one of the 2 doors with goats in them is 50%. Hopefully that makes sense too. There's really no distinction why he should choose one or favor one over the other. So we're going to write down that the probability that he opens door 2, given that we know the car is in door A, or the probability of B given A, is 1/2. Okay, there's one more term that we want to consider now, and this is the trickiest term, and it is the probability of B. But what does that really mean? So the probability of B is asking what is the probability that Monty opens door 2, but with no conditions, which is what makes it hard, because we don't have a specific scenario. But what we can do is enforce a specific scenario by adding the 2 scenarios that we do have. So either there's a car behind door 1, or there isn't. And so we can say, okay, so what is the probability that door 2 is opened by Monty? Door 2 is opened by Monty, given that the car is in door 1. So that's the probability that the door is going to be open if there's a car in door 1. We actually just computed that, right? So we just computed PB given A. That's already done. But there's another scenario, right? There's another option where the car is not behind door 1. It's rather behind door 2. And so I'm just going to indicate not with this little, dash over the top of the line. And the same convention is being used here as well. So the car is not behind door 1 multiplied by the probability of door 2 being open, given that the car is not behind door 1. So this is the total probability that door 2 will be opened, right? Because if we consider the fact that the probability that the car is behind door, the door 2 is opened, given the car is behind door 1, and multiply that with the probability that the car is in fact behind door 1, that gives us the total probability of that sequence of events happening. But then what is the probability that the door is opened if the car is not behind door 1 times the probability that that is actually true gives us the probability of that part of it happening. And sum them together and you get the total probability of the door 2 being chosen regardless of where the car is. Just in general, what is the overall probability that door 2 is chosen to be opened by Monty? So we're going to break this up into 2 subsections. We've already done the first one realistically. P of A, we already have computed. That's 1/3. So that's very simple. We can just plug that right in here again. We don't need to recompute it. And PB of A, we've also just computed. That's 1/2. But for illustrative purposes, what we're going to do is we are going to say that we know, so that, again, that does not need to happen. But what's actually a little bit more complicated is this one over here, because this actually further decomposes into 2 sub scenarios. So this one, very trivial. We've already basically computed the 2 terms involved in that. But for this second term here, the fact that the car is not in door 1 actually leaves 2 possibilities, right? It could either be in door 2 or door 3. And again, the labels are actually arbitrary. So there's a way of doing this without considering, specifically whether it's in door 2 or door 3. But I think it's just a little bit more illustrative to break it down this way. So in scenario 1, the car is not behind door 1. It's rather behind door 2. So Monty then has no chance of picking door 2, right? He can't reveal that the car is behind it. He always chooses the door with the goat. So the probability of him choosing this door is now equal to 0, right? There's no chance that he chooses door 2 if the car is behind door 2. Other scenario, the car is behind door 3. And if the car is behind door 3, well, then there's a 100% chance that he's going to choose door 2, right? Probability is 100%. Because he can't choose door 1. This will never happen, right? He will never choose door 1 because that's the door you select. That's the assumption we're going in with. Again, label's arbitrary. It could be any door. You could label the other ones accordingly. Just choose whatever door you picked initially to be door 1. Door 1, he can never pick. That's the door you picked. That would ruin the surprise of what's behind your door. And he can never pick a door with a car behind it. Always a goat. So if the car is in door 2, he can't pick it. The probability is 0%. And if the car is in door 3, the probability is 100% that he's going to pick door 2. So those are the two sub-scenarios. You can see that the options work out to be quite simplified, 0%, 100%. One thing is just going to completely cancel out. And we can specifically now write this whole thing as, so this is, again, going to be the probability that Monty picks door 2 with no restrictions on it. So we've already filled these in. The probability that the car is behind door 1 is a third, multiplied by the probability that if the car is behind door 1, he chooses door 2 as being a half, which we already computed. And now the second more complicated term is going to be a composition, right? So first of all, what is the probability that the car is not behind door 1? Well, the probability that it is a third, so the probability that it's not is 2/3. The other, it's the complement of that, right? So 2/3, there's 2 doors it can be behind that's not door 1. So the 3 doors, probability is 2/3. That should hopefully make sense, that there's a 2/3 chance that the car is behind some door besides door 1. And that's coming directly from here, the probability that it's not behind door 1. And then we're going to multiply that by the probability that he chooses door 2, given that the car is not behind door 1. And these are our two scenarios here. So what that's going to look like is the probability that he chooses door 2 is 0% multiplied by, well, how likely is scenario 2 to happen, and how likely as opposed to scenario 3 happening. Well, there's really no distinction between the two doors, right? There's nothing special. The problem is kind of symmetric in that sense. There's no difference between door 2 and door 3 in the likelihood of whether the car is behind door 2 or the car is behind door 3. Those are equally likely possibilities. So we're going to assign that a probability of a half, right? The car could either be behind door 2 or door 3. Recall, this is not with any kind of new updated information. This is simply saying, what is the likelihood the car is behind door 2 or behind door 3 right from the get-go? There is no additional assumptions being made here, so there's no trickery happening. All we're saying is the car can either be behind door 2 or door 3. Remember, this door 1 is no longer an option because it implies the fundamental condition for this is that it's not behind door 1, right? Any door besides door 1. That then leaves an equal probability that's behind the other two doors, so it's 50% chance it's behind door 2. Now, what's the chance it's behind door 3? It's the same chance it's behind door 3. But what's the probability that if the car is behind door 3 that he will choose door 2? Like we said, 100%. So again, I'm just going to draw some numbers, kind of draw where this is coming from. So 100% times half the probability that the car is in fact behind door 3. Okay, so what that works out to be is it looks pretty ugly, but it'll simplify down pretty nicely. So this is 1/6 is these two terms here, plus 2/3, the 0 cancels, and so we're just left with a half. So this works out to be 1/6, and then these 2's cancel over here. So 1/6 plus 1/3, and that leaves us with a half. Okay, so now we have everything that we need to be able to fully plug everything into Bayes' formula and get our answer. So the probability of A with, I'm just going to quickly go ahead and copy Bayes' formula so we can see the terms and I don't have to keep scrolling up and down. And I'm just going to grab that and put that over here. Okay, so the probability, so remember what we're computing here. We're almost done. The probability that A happens, event A happens, being that the car is behind door 1, given that we know Monty opened door 2, is the probability of B with respect, or the probability of B given A, which we've computed as a half. So we just put that over in 1/2, multiplied by the probability of A, which we know is a third, all over the probability of B, which we know is a half. We just spent quite a bit of time working that all out, and we simplified down to the probability of B being a half. So we notice that the half and half terms cancel, and that gives us a final result that the probability of A given B is a third. And that's our answer. So it's pretty cool that it matches up exactly, because remember, what is this term saying here? Well, the probability that the car is behind door 1, given that Monty opens door 2. And to generalize that, because you might be getting confused by why it's door 2, it can be said the probability that the car is behind the door you've chosen initially, which we've labeled as door 1, given that Monty opens a door with a goat behind it, which we've labeled that door, whatever that door would be, as door 2. Remember, we've actually considered both possibilities through all of these steps. Over here, we have counted for the fact that it's not necessary that he picks door 2. but because we've accounted for the fact it's an arbitrary label. And so with all of that, we finally get that if you choose a door and Monty opens another door with a goat behind it, the probability that the door you have chosen is actually the door with the car behind it is a third. So that means the probability that the door, that with the car is not behind the door you've chosen. So it's not behind door 1, it's going to be the complement of that, which means that is 2/3. Now remember the scenario, if you have 3 doors and your car is not behind door 1, Monty has opened door 2, there's a 2/3 probability your car is behind door 3. Another way of phrasing that, there's a 2/3 probability that the door that you did not choose initially and the door Monty has not opened has a 2/3 probability of holding the car. And that is the same result we've gotten here and here. So that proves through you mathematically now as well, as long with intuitionally, hopefully in the beginning of this video, that there is a 2/3 chance, there's a greater likelihood of you getting a car if you switch doors rather than sticking with your guns and choosing door 1, which only gives you a 1/3 chance of getting the car. Hopefully that was insightful, and hopefully you were able to understand that both from the Bayesian perspective as well as just from stepping through all the different possibilities. And thank you for your time, and thank you for watching this video. Have a good day.